All right, so I'm Rich. If you haven't met me before, the handsome gentleman right next to me, his name is Dylan. So we're gonna be your TAs for the remainder of this semester. There'll be another handsome gentleman by the name of OD. He'll walk in. No, yeah. It is hard.
Okay. So question one's asking, which of the following does not fit the definition of a Bronsted acid? There's like 3 different definitions of types of acids. Do you remember the first one we ever learned? Yeah, so it's like Arrhenius. And basically, these are just whenever an Arrhenius acid-base reaction is if you mix an acid like HCl with sodium hydroxide, you get a salt and water. But that's the basis of Arrhenius. And then the next one we learned was Bronsted. And the main thing about Bronsted acids and bases are what? What's the surrounding principle or the principle that surrounds Bronsted acid base chemistry? Yeah, protons are being tossed around, okay? So similar to the one we just had here, a proton is being lost from hydrochloric acid and is being gained by the OH, the hydroxide anion. So this is proton donor / acceptor. And the donor is which one? The acid or base? Acid, right? And the acceptor is the base. So we should be, the Bronsted-Lowry acid should be losing a proton and the base should be gaining a proton. So looking at number 1, which of the following does not fit the definition of a Bronsted acid? So the bottom line is, if a Bronsted acid is donating a proton, what should it have? It should have a proton to donate, right? So which of these does not have a proton to donate? C, carbon dioxide. Sweet, that was a very easy one. You're probably hoping that you get a bunch of these on your test. What about 2? Let's see, in the reaction of bisulfate reacting with sodium hydroxide produces sulfate and water. The conjugate acid base pairs are what? Okay, give you a second to look at that, discuss with your neighbors. And we'll talk in like 30 seconds.
I didn't read the question. I just looked at the first one. Reaction.
Okay, Patrick's already jumping ahead.
The bases are.
Go ahead, Patrick. So an acid is something that, let's just say, HSO4 minus is playing the role of what in this reaction? Acid. So the conjugate base, so an acid always produces a conjugate base. I'm gonna denote that as Cb. Conjugate base is it's the anion that results when you lose that one proton. So if bisulfate loses a proton, what does it become? SO4 with 2 minus. So the acid is bisulfate, the conjugate base is sulfate. So without even looking at the rest, without the hydroxide of water, we should be able to eliminate at least some of the answers. So the first pair should be these 2 as our acid and conjugate base pair. So we can eliminate B because that says bisulfate and hydronium. You can eliminate C, D, and wow, look at that. E. You all agree that it's answer choice A?
Yep. Well, you see at the bottom, but
I agree. So A is the right thing here, but that corresponds to answer choice C.
I don't
So
like
we gotta be careful about that. Anyone else not understand that or any questions so far? No questions? We all get the idea behind acid-base chemistry. If not, do 3 and 4. And I'll give you all 30 seconds. If you haven't done it already. And then I'm gonna ask someone to explain it.
One knows what the job.
Oh, thank you, yeah.
All right, does anyone want to explain what they chose and why they chose for question 3? Audie, you don't know?
I
What?
mean, usually don't let me answer, but
Well, because no one else.
it would be, well, I put B because the conjugate base is the byproduct of an acid donating its.
Yeah.
proton.
So it's asking for the conjugate base of HPO4 2 minus. If it's asking for the conjugate base of that, that means this is playing the role of what? The acid. So HPO4 minus 2 minus is our acid. And to write our conjugate base, you remove what? The hydrogen more, well, a proton, right? Because the conjugate base is keeping those electrons. So you're really just taking a proton. And we denote that just by losing a single proton, so single H, right? So this would be PO4 with the 3 minus charge. So like Audie said, answer choice B would be the conjugate base for that one. And identify the conjugate. I'll let Rich do this one. What did y'all get for answer or question 4?
All right, got some E's for elephant in the room. So let's address the elephant in the room. All right, conjugate acid for HCO3. So what's the key difference between a conjugate acid and base? There's one hydrogen difference. There's a 1 H difference between your conjugate acid and your conjugate base. So your conjugate acid of HCO3, if it's a conjugate acid, do you add a hydrogen or do you remove hydrogen?
Add.
You add a hydrogen. So if you add a hydrogen, this is H2CO3, and you also add a positive 1 charge. So the negative and the positive cancels out, and this becomes neutral. So the correct answer is indeed H2CO3.
I have a question.
Yeah.
It is possible to add more than 1 hydrogen, right?
What was that?
It is possible to add more than 1 hydrogen or lose more than 1 hydrogen.
You could only go.
So not at once. So like you can't add like 2 or 3 hydrogens at once, but say for example, something like H2SO4, a polyprotic acid, you can lose it over the course of a series of reactions. So it is possible to take off both of the hydrogens, but it's not possible to like add like 2 hydrogens at once. Or not yet, not for stochastics.
Yeah, you can, like, I just.
Any other question?
Right. Which of the following is not a conjugate acid base pair? Right. There are some C's and there are some D's. So let's go through it. So the main thing, right? Conjugate acid, conjugate base, 1 hydrogen difference. So we got to look at where there is not a 1 hydrogen difference. So for A, there's 1 hydrogen here, 0 hydrogen. 1 and 0, that's a 1 hydrogen difference. So you can cross it off. For B, there's 3 hydrogens here, there's 2 hydrogens. Sounds good to me. For D, there's H2O, H3O plus, that's also 1 hydrogen difference. And then for E, there's 2 hydrogens here, 1 hydrogen here, it's also 1 hydrogen difference, cross that off. Then for C, we have H3PO4 and HPO4 2 minus. That's 2 hydrogens difference. And also the charge on this is, or the charge on it is correct, the number of hydrogens. Wait, never mind, other way around. H2B, whatever, y'all get the point. So 3 hydrogens here, 1 hydrogen. All right, questions on that?
Yeah.
Wait, doesn't it have to be acid to base, not base to acid?
I mean, not necessarily, because it's asking here, like, which one's the conjugate acid base pair. So like, it's asking like, which one's the acid, which one's the conjugate base. They can be arranged in any order as long as they're, within 1 hydrogen of each other. Right.
So you guys want to-
Any questions on that one? Right. Now it's time to bust out your calculators. Determine a pH of a potassium hydroxide solution by mixing 0.251 grams of potassium hydroxide with enough water to make 1.0 times 10 to the 2 milliliters of solution. All right, I'm gonna give you all about, say like 2 minutes. We meet at approximately 5:15 p.m.
No graphic calculators. We're just seeing it as a general thing about the class. Okay, like, what it tells you. What? You're talking about for the inductive effect?
Yeah.
Bro, yeah,
But not for this.
I mean, I don't think so. The donating.
What else? Oh, that's. Hydro, that's a little more.
A toxic.
It
It depends on what it, if it's attached to like a conjugated areas, which means it's just some pi bonds, which means you can donate through resonance, then it is a donating. But if there's no pi bonds, it's strictly oxygen is more electronegative, it's gonna withdraw.
But what other electrons have we?
Nitrogens could be like amine, so like NH2 or something. I mean, for the scope of this class, I didn't know anything.
Yeah.
Videos.
Okay, I didn't know any electron donating, withdrawing groups, whatever, until I got to alchem.
Okay, so it's fine if I don't know it.
Yeah.
All right.
So, and plus Dr. Thomas can make it with us, so we didn't need to know it for our test. I don't think. I heard. That's tough.
All right, I'm gonna give you all 1 more minute, because I'm nice. But yeah.
Oh, thanks so much.
You just five and six.
This, everyone drops space like this problem. Everyone's really.
Okay, I got a question for y'all. Did Zapata teach y'all percent dissociation of a weak acid?
Did we do that? He talked about it, but then he didn't like, oh, you still really need to know these.
He taught us about vitamin D deficiency. That's what we're-
Remember the thing I said, you don't want to get a 96% dissociation for a weak acid?
Yeah,
Remember that?
yeah.
That still holds true. You do not want to get a 96% dissociation for a weak acid. Right?
Yeah, exactly. All right.
All right, that's about time. Determine the pH of a KOH solution made by mixing 0.251 grams of KOH with enough water to make 1.0 times 10 to the 2 milliliters of solution. Or if you want to be not fancy, that's 100 milliliters. All right. So what was y'all's first step in solving this out?
grams, moles.
4 grams to moles. That's what I would have done. 0.251 grams of potassium hydroxide. And what is the molar mass going to? 111? 56.11. 56.11 grams in every 1 mole. But wait, you always, for pH, what do? You always negative log what value? Or the hydronium what?
Concentration.
The concentration. So you need to get it into units of concentration, which for our case is molarity or moles per liter. So we can just divide this value by 0.1 liters to get our answer in molarity. So if we solve that out, we will get 0.0447 mole. Now, is this a concentration of H3O plus or OH minus? OH minus. So if we negative log this value, what will we get? Yeah, so we negative log our POH is going to be equal to the negative log of 0.0447. Now, some of you are probably thinking, Rish, we didn't do a rice table. Can anybody tell me why? Strong base. There's no need to do a rice table. You assume that it completely dissociates. So if you negative log that, you get 1.35 as your POH. So what do you have to do to get your pH from here? 14 minus. So 14 minus 1.35, you will get 12.65 as your pH, which corresponds to answer choice B. All right. Now, for 7, sort of the same principle, right? Is HCl a strong or a weak acid? Pretty strong. So because of that, you need to do a rice table. Exactly. So we're already given our concentration here, so it's good to go. All we have to do is just what? Negative log of 0.002. And if we do that, we shall receive an answer of. So
I have a question. Why didn't we multiply by the 10 ml?
because we're already given concentration anyway. So if we're already given our concentration, the 10 milliliters at that point is extra information. So if we do that, we will get an answer of 2.698, which corresponds to 2.7, which is answer choice A. All right. Now, number 8 is kind of a tricky one. So I'm gonna maybe give y'all 2 to 3 minutes because y'all, from what I've heard, have not gone over percent dissociation. So remember, right, the formula I will say for percent dissociation. I do not know how to spell this word. Dissociation, something like that, is equal to the H3O plus concentration that you get from the rice table over the initial concentration of HA times 100%. Yeah.
Nice. 2 minutes and counting.
Huh?
Tyler.
Yeah.
Remember what you do to get pH. Remember how the numbers.
Oh, thank you. I appreciate it. Yeah,
Wait,
for real.
how do you tell
Highlight,
yes.
This is what time did you get Aguilar next semester?
Oh, Monday, Wednesday.
He has 2 classes on Monday and Wednesday.
Wait, is it the one that ends up?
Yeah.
4 p.m. now?
Yeah, they're
He
like.
has 2
late.
classes one day.
Oh, I thought you. Yeah, Tuesday, Thursday.
You couldn't teach an OChem 2 class?
Maybe.
Scared.
That would be, this is the other good looking TA that you're gonna have.
The other handsome gentleman.
I bet. Hanson, same thing. Oh, I wasn't. The more I think about it,
We're gonna do.
I want to be a TA for OChem too, not OChem one.
Well,
So
we do for like, you know.
I would, but it's so the first part of OChem one is the most boring thing ever.
actually, like, determine the relationship between these 2 components.
Isomers.
It's in multiple choice, so like you have to write it out.
If you have Aguilar, it's gonna be majority multiple. I mean, he can tell you because he just took an exam. But yeah.
Wait, multiple choice?
For Aguilar, the rest of the exams.
Yeah, it is also.
All right, Rich, how do you go about this problem, Rich?
All right, so 8.2% ionized. What does that mean?
8.2%.
Yeah, the percent dissociation is 8.2%. So to convert this to a decimal, as I heard some people asking, you do 8.2 divided by 100. And to do that, okay, so you get 0.002 0.082. Now, this is equal to we need to find pH. So what does that tell you? What do we need to solve for first?
H3O plus.
Our concentration of H3O plus. So we're gonna call this H3O plus concentration X because we don't know what it is. And then this is gonna be over our 0.0055, which is our initial concentration of HA. So if we multiply that out, we will get 0.0055. We will get our hydronium ion concentration is equal to 4.51 times 10 to the minus 4. Now this is equal to hydronium ion concentration. How do we get to pH? Yeah, so our pH is going to equal negative log of 4.51 times 10 to the minus 4. And if you do that, you will get an answer that is
An answer.
which is 3.35, which corresponds to answer choice. Questions on that? Questions on how I got there?
Start with number 10. You can start with number 10. Well, I mean, I could, but I'm trying to.
Here, I'll go number 9 and you guys 10.
Yeah, pick up 10.
Yeah, sure. All right, Dylan will take it over with number 9.
BTA is somewhat, but it's cool. All right, arrange the acids HOCl, HClO3, HClO2 in order of increasing acid strength. Okay, these are what was the answer for 8 again?
A was 8, 3.35.
All right, what kind of acids are these?
Yes.
Oxyacids. And what are the things that determine the strength of an oxyacid? What are the 2 factors?
Number of oxygens. Yeah.
Number of oxygens. And then the second one is the central atom of this acid, and it's determined by the electronegativity of it. So central atom electronegativity. All right, so hopefully we all remember our electronegativity trends. Do we remember that? So if this is our periodic table, the electronegativity increases as we go from left to right. So En increases. And then if we go down, does electronegativity increase or decrease? Decrease. So En decreases. So you should be able, with the periodic table, you should be able to figure out which one's more electronegative, right? So we can see that all these central atoms are the same, right? They're all chlorine. So that's not the thing that we care about. But we do realize that the amount of oxygens differ. And if you increase the number of oxygen atoms, you increase the acidity of the acid, therefore making it a stronger acid. So the one that should be the strongest acid should have the most amount of oxygens. And that, in this case, which one is that? HClO3. So HClO3 should be all the way to the right. So we can go ahead and eliminate B, C, and D. And if we know that if we're just going down, we know that the second strongest one should be the one with the second most amount of oxygens. So that would be HClO2. And then lastly, HOCl or HClO. So answer choice A is that one. Do you have a question?
Different amount of oxygen.
Different, okay, so if it's different amount of oxygen, so like HBrO3, HClO2. Typically, let's see, it's a hard one when it's like this, just because you don't know which one plays a bigger role, either the inductive effect of the central atom or the resonance. I'd probably say the resonance plays a bigger role. But you probably wouldn't be giving anything like this. It's usually same across the board, either all constant central atoms or same amount of oxygens, different central atom. So that's usually what you would see for this class. But if I had to guess, I think this one would actually be more acidic. You can check that. Just because I'm pretty sure the resonance effect has plays a stronger role in acid acid strength. All right, if there's no questions, I'm gonna pass the pad over to OD.
All right. So for number 10, this is a titration type question or a buffer, but like the way you'll calculate is kind of similar to titration. So we first need to understand what's going on here. So let's see what's going on. We have a buffer. The total volume of the buffer is 0.75. And then you can see that you have this concentration of benzoic acid and this concentration of sodium benzoate, and you're adding in 340 ml of HCl. So whenever I do these kind of questions, the first thing I like to do is write out what's happening. And as we can see here, this is benzoic acid and this is sodium benzoate. Oh, okay, yeah, that's nice, but it's good space. Okay, so the way to go about these, first, let's just write what's going on. I don't really like to write the whole benzoic acid. Let's just refer to things as HA and A minus. So what we know for sure is you got HCl being added. And if I'm adding HCl, is it going to react with the sodium benzoate or the benzoic acid? Which one? Because sodium benzoate is a what? It's a base, exactly. So if you're adding in HCl, it's going to react with the base. So instead of putting sodium benzoate, I could just put A minus because we understand that's a base. And we know that in this buffer, if you're reacting acid with the base, you're going to form more benzoic acid. I'm just going to refer to it as HA. Is everybody with me on that? Cool. So from here, all we have to do now is we need to determine what do we have left after we add that. So we need to first find our initials. So our initial mole of the HA, the benzoic acid, all you have to do is multiply the liters times the molarity. So 0.75 times 0.3, and you'll get an initial mole of 0.225 mole. And remember, this ice table is giving you moles, not molarity, because this is where mistakes can be made at the end. So now we can get the A minus the initial. Initially, there was a concentration of 0.35. You need to do the same thing and multiply it times the liter of the entire solution times 0.75. And I'm getting an initial mole for the A minus to be 0.2625. 0.2625. Cool. So now from here, we need to find the change. The change is where the HCl comes in. So we need to figure out how much moles of HCl came in. So that 340 milliliters immediately turn out to liters, 0.34, and multiply that times the concentration, which is 0.35. And you're getting a change, or like what you added to the HCl. This is how I write my ice tables, 0.119. So when you put in that HCl into the buffer, you're going to be taking away some of your base and you're going to be adding more to the acid. So you're going to subtract that 0.119 from the A minus, 0.119, and you're also going to add to the base. So that's going to be plus 0.119. Everybody with me there? Okay. So then here, we need to get our equilibrium. So let me ask this. Do we still have a buffer? Why?
Still A minus.
There will still be A minus left over. And I can see, Daniel, you're asking why is it 0.19? So remember, this ice table is more moles because at the end, I'm going to turn everything back to molarity, but let's work with the moles first. So the reason why it's 0.19, you can see here that it's 340 milliliters, 350 M. So you just need to turn that milliliters into liters. So that's going to be 0.34 L. You multiply that times the concentration, 0.35 M. And that's going to give you 0.199. And I'll do it again to make sure. 0.34 times 0.35. I'm getting the same thing, 0.119 moles. Cool. So now we just need to subtract that. So 0.2625 minus 0.119. I'm getting leftover A minus to be 0.1435. And then now I need to add that to HA. So 0.275. Is that 27? That's 225, right? 0.225 plus 0.119. And that's giving me 0.344. And this is now my equilibrium of moles, but we got to remember, I'm going to now throw this into the Henderson-Hasselbalch, but Henderson-Hasselbalch, does it deal with moles? It deals with concentration, right? Of what over what? Base over acid. So let me now convert these moles into concentration. So I need to now divide this by the total liters, which is going to be your 0.34 liters plus your 0.75 liters. And that's giving me a total liter of, I believe that's going to be 109, but let me make sure. Was 1.09, yeah, liters. So now it's gonna divide that from both 1.09 liters. And that's gonna give me a concentration of base to be, let's see, 0.5, 1.09. That's giving me a concentration of base 0.13165 m, and then concentration of the acid to be 0.344 over 1.09. That's giving me 0.315. I'll call it 560. 560. And is everybody with me? Am I losing anybody? Be honest. Okay, so now what's going on?
Yeah.
So where did I lose you?
Why didn't we use the equation pH plus, what do they call it, equals?
Oh, pKa plus the log. So it's because if you threw it, because first you need to determine what buffer do you have left. So now that I have like my concentrations left over, I'm about to now throw in the Henderson House buffer.
Okay.
Yeah. So does the ice table make sense? And if anybody has a different way, I'm actually interested to know. This is how I do them. But yeah, let me know after, I guess. But yeah, so this is how I do it. Now that we have our concentrations, now you throw it into the Henderson House buffer. So how am I going to get my pKa? I have it, right? Negative log of what? So 6.5 times 10 to the negative fifth, Ka is right here. And that's going to give me a pKa of 4.187. So now let's throw Henderson House buffer. pH equal 4.187 plus the log of the base. So what's the concentration of the base here?
0.
What's the concentration of the base? Okay, fuck, it's all right, we'll live. 6.5 m over concentration of the acid, help me out here. 0.31560 m. And then now we're gonna get our pH of, let's throw it in. So plus the log of 0.13165 over 0.31560. That's giving me a pH of 3.81, about 3.81. So the answer to that is E. That's gonna be your lengthy one. I'll just say this, if you're taking this test, like low key, the type, not titrate, but just these kind of ones, I'll throw them in the back, I'm not gonna lie. So that's, yeah. Like make sure you bank on the easier ones. Like if you have like a, what kind of solution will this make? And you have a sodium and nitrate, you know, that's gonna be neutral. Like just stuff like that, get your easy bank points because they're worth the same amount. But yeah, any questions on this one? Everybody with me? Okay, so let's go to number.
You had a question?
Yes.
Yeah, go ahead, my bad, I missed you.
Would you still get the same answer if you converted it to molarity first before you like do all of it?
Yeah, like actually what you could have did here was you could have turned them to moles. See how I turned it to moles, like I was trying to circle it right here. That you see this 2625?
Yeah.
What I could have done here was I could have immediately divided this by the total liters of that added HCl. So if I added that 0.75 liters to the 0.34 and divided it by that, I don't know, man, I was just like, no, but you could have gotten molarity, yeah, and then that would have saved you conversion, however you want to do it. But yeah, I don't know if that's what is that what you were asking me?
Yeah, that was what I was
Okay.
asking.
So yeah, you could have did that. You get the same answer. Yeah. Everybody with me? All right, so let's look at number 11. So number 11, which of the following compound is more soluble in NaCN than in pure neutral water? So first thing I'm gonna say is, y'all remember, y'all gotta be a little strategic here. They're taking the acid-base exam. So they're probably gonna be asking you acid-based questions. So who's gonna tell me? NaCN, we looking at an acid, base, or neutral?
Base.
Base, what's telling you that? What do I know about the Na? Spectator, neutral. What do I know about the CN? So it's basic, exactly, negative charge. So this is basic. So first of all, if I know something's going to be soluble, then that means it needs to dissociate. If it needs to dissociate, it needs to probably react. So I look at this one and I'm going to be looking for, if this is basic, what's going to react in a base? A basic solution. And that's it, right? So let's go through these answer choices and let's try to narrow them down. MgOH, what are we looking at here? Basic, acidic, or neutral? Basic. So we already know that's wrong. AgBr, basic, acidic, or neutral? Acidic, which part of it is acidic? What's telling you guys that? The Ag, right? Exactly, because it's not a group 1 or group 2. So I'm gonna leave it. NH4 ClO4, acidic basic. Acidic, so I'll probably leave it. Ca3PO4, what are you looking at? Basic, so probably take that off. CaCO3, what are we looking at? Huh? Acid? Who said acid? Okay, fine. It's CaCO3. So it's basic. All right, so I'm down to AGBR and NH4 and ClO4, and this is where my good friend Rich came in hand. And he bring up a pretty I can't think of the word, but he came with a pretty good explanation. So what are you guys going with? Huh? Somebody, okay, just raise your hand. Somebody give me something, man. Throw me a bone. Huh? B. Why you going with B?
He told me, but-
Okay, no, you're gonna spoil it. Anybody else? Somebody give me something.
Isn't B like a strong acid, like HBr?
HBr, so what does that tell you?
That's about the ion.
Interesting. What about it?
I mean, HClO4 is a strong acid if you go by that logic. as
So the
well.
ion's like HCl, is like, it's like NaCN is like 1 to 1, HBr is 1 to 1. Whereas like, oh no, it's still 1 to 1, so never mind, I don't know. I was guessing.
No, no.
Keep throwing out the idea.
Exactly. Keep throwing them.
I mean, it's good. Like whatever process y'all are going through right now, I went through the same thing when I was trying to figure out this question.
Process of elimination.
It's shorter.
Huh?
It's like less, it's shorter.
Interesting. That's a good point to make. Anybody else? So, okay, so this is where the little Gen Chem 1 come in. AGBR. So what do we know about silver? It's typically soluble or insoluble. I could bring out my whole solubility rule sheet. Remember AgCl? Was that soluble or insoluble? You guys remember? Oh shit. Yeah, it's insoluble. So like it's insoluble. So like basically whenever silver is reacting with halogens, it's typically insoluble. So the reason why I'm bringing that up is the question is which one of these compounds is more soluble in this? So we know NH4 and B and C are fairly soluble because they're acidic. But one of them in neutral water is not even soluble, and it's the AGBR. But in the NaCN, it can be soluble because it's acidic, and also it's just more soluble in the NaCN because it's not soluble in water. So the answer here is B.
Why would it not be C?
Because C, what do we know about ammoniums? Oh, no, let me not misquote though. I believe ammonium's always soluble or ammonium's always soluble. So is there really a difference between putting ammonium in NaCN or in water? Aren't they both gonna work?
Yeah.
But the AGBR, it won't work. So therefore AGBR will benefit better.
You have a question.
Yeah, but why are we going with ABR if it's insoluble when we're trying to find a more soluble?
I'm trying to figure out which one is gonna make it more soluble with this new solution. So in regular
The solubility increase.
in neutral water, you're not gonna get any silver you're gonna get very small amount of silver bromide to dissolve. But if you throw it into sodium cyanide, because it's acidic and it's reacting with the basic solution, it's gonna cause it to dissolve a little bit more readily than it would in neutral water. Whereas ammonium perchlorate is very soluble in neutral water, meaning if you throw it into, it's an acid, right? Ammonium perchlorate, it's acidic salt. So if you throw it into a basic solution, it's probably just gonna dissociate just as well. Maybe not notice, maybe a little better, but not noticeably.
Anybody else got a question on that one? So just remember to really think on this exam, take your time with some of these. Okay, so number 12, KSPs. So let's look at it. We have molar solubility, CaF2, 0.25 M solution, Na and F, NaF, my bad. And KSP is CaF2. So the first thing I'm doing is probably going to break that down. So we see KSP. We have Ca and F2. So Ca, how many Ca's do I have? 1, 2, 3, 4, how many? 1. So I'm just going to leave that as X. But my F2, how many F's are there? So what's the proper way to notate that? Annotate that, sorry. 2x squared. And did I lose anybody with that? Okay, so 2x squared. But then one thing to note here is that it says 0.25 M of F. So we already have some F in it. So we already have F in it.
Yeah, put your fingers like this.
Oh, really? Oh, shit. All right, so yeah, so you see that as NaF, right? Long story short, You see this 2x squared, is that corresponding to the CA or the F? To the F, right? Because it's 2x squared because there's two F's. So I'm gonna now add that. So I'm gonna bring this down. KSP is equal to X 0.25 plus 2x squared. Did I lose anybody with that? Yes.
So are we just doing this to avoid doing ice tables?
The KSPs don't really evolve as tables, to my knowledge. from what
I
know.
mean, this is like sort of an ice table, but not really. It's more of like a shortcut.
Shorthand ice table. Yeah. Oh, I see what you're saying. Oh, okay. I didn't. Yeah. Yeah, shorthand ice table. Yeah. I see what you're saying now.
I'm like,
Yeah. Oh, that's just how you set these. I really don't remember how to explain these shits. Like, this is how you set them up.
Okay, for,
This is gonna get a
Yeah.
demonetized.
so for this, right, like CaF2, that's normally a solid, right?
Yeah.
So a solid you don't include, right, in your equilibrium expression. That's why you sort of set it up that way, because it's just your products and not your
I
reactants.
get it, it's just that more so who's like, people are a little fast, just to.
Oh, my apologies. My bad.
Felt
My
like
bad.
my brain's trying to keep up with what you're saying, so that's all.
Yeah. I mean, it's because I'm not really saying much because it's like, this is more of like, just like, you just have to memorize how to set these shits up, man. Yeah, like, I don't,
You just said that.
is there a way to explain these? Yeah. I don't know how to explain how to set up the expression room.
Right, not time to actually edit my videos now.
Oh, wait, hey, no curriculum? Is that what it is?
Yeah.
Oh, okay, I'll keep this together. My fault.
I mean,
Oh,
I don't care either way. I thought we're earning any money from doing this anyway. Like,
you never know, bro. You never know.
Eventually.
Exactly.
Okay, so for a typical rice table, you start with your reactants and you write your products, right? So I'm just gonna go through it, so how you get to that.
Wait. Did we just move on?
No, it's the same question.
Oh.
Yeah, he's just set up the
Alright, so your initial, this is a solid, so you don't include that.
Yeah.
And then this is gonna be 0 at first, because right now you just dropped it in, there's nothing, right? Our change is gonna be minus X plus X, and what is this one? What is the fluoride gonna be? Plus 2X. So our equilibrium is going to be, we don't really care about this because it's a solid. So we only care about X and 2X. So if we put that into our equation, I think it was 0.25 for that point. That's right.
Yeah, that's what you should have done.
Oh, okay.
So 0.25. All right, so if you write your KSP equation, it's typically products over reactants. So it'd be the concentration of your, let's see, where is it? Yeah, concentration of your calcium ion multiplied by the concentration of your fluoride ion, but because squared, right? Because that's normally how you do your KSP equations. But because we're talking about molar solubility, every time you see molar solubility, it involves this little, that's when you start incorporating the X, okay?
Okay.
So that's, in that case, you change this to, change the width of my eraser. You change this to X, and then this one to 2X, because it's talking about what? Molar solubility. That's the only time we incorporate the X's in this. And because we had an initial concentration of 0.25, then you would put that here as well. So 0.25 plus 2X. So that's the way you would derive the equation. But typically, you just, when you're doing KSPs, you see how many ions it dissociates into. And that's your X's and your, that's your KSP equation. So it's a shorthand way of going, instead of having to do the whole rice or ice table. So I'll let OD go ahead and finish that problem.
Thank you, colleague. Not that we doing that, explain it way better. So, yeah, and at this point, we have the KSP set, but the thing is, they gave us the value. So we just need to, you see the KSP, we're solving for X. If we were solving for KSP here, there's two unknowns. We're only solving for the X, meaning they must have given us the KSP, which they did, because it's right here. 4 times 10 to the negative 11. Now, all we're doing is slapping it in place of the KSP. So that do is erase this. And then slap in that 4 times 10 to the negative 11. And at this point, all I'm doing is solving for X. And let's see what X gives us.
1.599 times
It gave you what?
10.
One more time?
1.5 9 repeating times 10 to the negative 10.
So here, that's about 1.60. So the answer here is D.
What?
Is it D? Sure.
Yes, you can.
You got an A, so was that, right?
You're so proud.
That's where it
Yeah.
Squared, right?
Is it correct?
No, yeah, some. Oh, shit, I forgot the square, I think.
Oh, you forgot this, okay,
Yeah.
let me try it now.
Yeah.
Isn't it this?
Yeah. It's in there.
Oh, yeah, it's 6.399
That's, okay,
times 10.
yeah, I'm getting that now, okay, that's, yeah, so
I forgot about the square.
that gives you X is equal to
What were you gonna say?
Can't forget about the square.
6.4 times 10 to the negative 4.
Oh,
Negative 10.
like
Answer here is A. That makes sense?
So typically it's like
And you.
this, right? Your KSP equation.
So it makes sense to everybody?
I'm gonna ask you.
So let's look at number 13. So this is a very similar question to the last one. So what do we know about NH3?
Solubility.
It's a base.
That's what
NH3 is a base, right?
Solving for X.
So
X is.
that means if we need something to dissolve in NH3, then it must be an acid, right?
So that's what you.
So we basically just trying to see which one of these answer choices is acidic. So let's run it through.
So.
A, neutral, basic, or acidic?
And then this one is 0.25 plus
Um,
2x. Incorporate into that
Neutral?
and-
Because you have a group 1 in nitrate, which is an anion, we have the strong acid. What about B? Neutral, acidic, or basic?
Exactly.
Acidic, so I'm gonna keep it, it might be. C, neutral, acidic, or basic?
So it's always solid 2 times.
Oh, so it's always just going to be.
Neutral, wait, so is C neutral or acidic? Or it's neutral or basic?
And
I'm gonna say it's
you
base.
gotta solve it out.
Basic?
KM's
Strong acid, SR comes back with strong base.
Okay, so why are you saying it's basic? Why are you saying it's basic?
Actually, that's correct.
Plus,
Yeah.
This is probably gonna be on your test, not this exact question, but the specific concept.
You go right up.
Why are you saying it's basic? Why are you saying, so who's going with, is anybody still going with basic?
Yeah.
Who? Nobody? Because guys, I think you guys are confusing, you guys think that you have this. Correct.
H2SO4.
H2SO4, but what's the conjugate base of H2SO4? HSO4 minus. So if you have SO4 2 minus, this is basic. This is neutral.
Huh?
That SO4 2 minus is not the conjugate base of H2SO4. You can't jump 2 protons. It's HSO4 by 1 proton.
You've only jumped.
Yeah, so it's so this right here is basic. This
Yeah,
is
it's like double the work for a normal.
that makes sense.
Yeah.
Oh.
So C is basic, yes.
Yeah, I was great.
So-
Doubt myself.
No, yeah, but I was trying to see if you explain why, obviously, yeah. So yeah, C is basic. Anyways, long story short, it can't react anyways. So CAF2, basic, acidic, neutral. CAF2, neutral.
Yeah.
So what do we know about the F minus?
There's certain like things. Based on the pH.
No,
It's
it's
strong acid. I don't know when it's not. It's basic.
It's basic. Yeah.
Yeah.
And then last MgCO3, basic. So the answer here can only be B.
Yeah, there'll be like Kas and then there'll be like indicators.
That's at least 14.
So you just.
Which is more soluble in acidic solution? So keywords, they're just looking for, what are they looking for here? A base. So KClO4, neutral, CuBr,
Minus is the conjugate base of HO3, meaning this is.
basic, acidic, neutral, which one? Acidic, right?
Yeah.
Okay, exactly, because the Cu plus,
It's the weak
FBS.
base at doing its job, so. A weak base is bad at that, so.
It's kind of both, isn't it? Let's think about it. What's HS? Is HS a strong acid? Huh?
The thing is.
Is that what I'm saying? Like HS is, yeah, so what are we going with here? Kind of both, right? You guys kind of see how it's both? HS, is that a strong acid? No, so it's kind of basic. Fe, I mean, it's a transitional metal. That's also acidic. So, we don't really know. D, PBI, acidic. And then E, NaNO3, neutral. So it's gonna be the strange FES.
So the three for the BA with H.
That's how you solve this.
Because H2S is a relatively strong acid, so HS
So
minus would
this
have a
tells us
relatively high K.
That you're dealing with a strong base.
So answer here
and then
is
strong
C.
acid. So this is gonna combine to make.
But he doesn't respond.
Go ahead.
Because the sulfide would react, sulfide is basic, right? So when that reacts with the
He
water.
dropped the lowest. We.
Make HS.
But I would say two, what about the FE?
AGI.
What is that?
No, I mean, I'm just like, it's another example
So
for why it's the answer.
HS
And.
I mean, yeah.
Yeah.
Yeah, that's basically what I said, the, like
Like,
the
if you look at
reverse
the
reaction. of
thing,
this.
yeah.
Yeah.
But just.
I think key ones y'all wanna go over.
Like how it works, it's able to like.
Yeah.
Huh? 17?
I have no idea. Like, I understand, you know, yeah, so like, I get the answer, but I'm like.
Oh.
Good.
Oh, I know.
Dude, like, handle it.
Like, I'm lucky it's.
I get.
Got it, but like.
I would.
So if we're forming a precipitate, what's KSP in relation to QSP?
If the Q, it's saturated, which means that. Right?
All the way around, so
Less than K.
if Q, the only scenario in which it doesn't form is if Q is less than K. That's the only scenario in which it can take. So that is if Q is less
I
than.
don't know when to use.
So Q less than K, no precipitate.
Let's remove my shoe.
No. Right out, let's write out our reaction. So PbNO3 goes to Na2S. Now, what is our precipitate going to be? If there is, like, what is our supposed
Which is.
Yeah,
relatively
PBS.
Strong. base.
PbS and then NaNO3?
Remember you-
So with that, we can say that precipitate, so we can narrow it down automatically to B and C.
Because
So it's either
still
yes,
acid,
the precipitate's PbS, or no, there is no precipitate at all.
Really strong base, so because it's a strong conjugate.
You just-
it's automatically.
Do that again. I
it's
would.
going to be base.
All right, so what will precipitate form? So if Q is less than K, that's the only Q, I should say QSP is less than KSP. That is the only scenario in which precipitate won't.
Weak acid. How do we go to weak acid?
How do you use that if you have two
That
separate?
and it's not a strong
like,
acid. That's the
like with
difference,
the
right? So it's a weak acid, but it's not one of the 6 strong acids. So
Fantastic question.
weak acid produces.
So I was just saying like off the like, that's what you go with.
a base.
However, here
Strong bases are.
it says 50 milliliters of 1.2 times 10 to the negative 3 molar PbNO3 and it's added to 50 milliliters of 2.0 times 10 to the negative 4 molar
Which means
NH2.
that CO3 minus.
So I guess the assumption you sort of make here is that this thing forms. So you do it as if this thing forms. So let's write out our KB expression for KSP expression for PBS. So PBS, kids, goes to what?
PB two plus, just it's X squared,
Yeah, PB2 plus and then
S2 minus.
S2 minus.
Oh, wait, wouldn't it?
Is the reaction balanced though?
He does some
Yes.
alkyls
Yeah.
on this, just saying.
I don't know.
Well,
Determining which
all
salt.
right, 1-to-1.
Acidic basic.
So now all that's left is you have to calculate the,
No, it's not.
Not
And
valid.
it's us because Na is missing a 2 and there's Na2S.
Yeah,
yeah, so slap a 2 right here. The nitrates are balanced. How's it balanced?
no, then you need to,
Wait,
wait, no, yeah.
but you're getting the KSP of the PBS because that's the precipitate that's forming. So you're really
Yeah.
only focused on that. So as long as that's balanced, then you're good. And since it's two plus two, right? That's it.
Pretty much.
Yeah, so that's
All right. So now from here, you just identify your concentration of both lead 2 plus and your concentration of S2 minus. So what are those values?
They give it to 1.2, -3.
Yeah, so that's 1.2 times 10 to the negative 3, and then that is 2.0 times 10 to the minus.
This one,
So if you solve it out, what will you get? QSP or KSP?
like an exponent.
Yeah.
Yeah, QSP, because it's nowhere in the problem does it say that
That's the way I would.
in equilibrium.
So it's like, then how, what would you compare it with? If they don't give you a table.
That is a good question. So here's the thing. So lead two sulfide, is that normally soluble or insoluble? Yeah, sulfides are normally soluble and lead's one of your exceptions. So if that's the case, your KSP will be very, very small. We're talking something like 10 to the negative like 15 or something. So if that's the case, if we solve out our QSP, what will we get?
If your calculator, Rich, your superior calculator.
-7.
All right, you get 2.4 times 10 to the negative 7. So what does that mean? Our QSP is greater than KSP.
Need more, yeah.
So if that's the case, then you need more reactants because the reaction will go to left, meaning that yes, indeed, it will precipitate more form. So the answer is C.
Should I see, did I make a statement?
Yeah.
So I would have just gone with C because of PBS, that's like, after I write out the equation, I would have.
Well, I just converted all of those to moles and then I was like, oh, well, if I subtract this and this and I get excess, I had excess with PBS for. You, yeah, no,
I would have just,
I don't know, something like that.
Well, this is the proper way to do it. This is like the certified hood classic way of doing it. So first, you have to find QSP because that's what they say at equilibrium, because you have to compare Q and K, see if there's precipitate or not. So you don't know what K is, but using your deductive reasoning, you can say that since it's insoluble normally in water, you can say that the KSP will probably be like a really, really low value. Something like 10 to the negative 7, that'd still be slightly soluble, but for lead 2 sulfide, that thing is not budging an inch. Like that thing is not soluble whatsoever. So because of that, it's probably lower than that. So since QSP is greater than KSP, the reaction would go to the left, meaning that there would be more precipitate. So the answer would be C.
I agree. Give KSP. Might as well give him KSP. That was
Yeah.
annoying.
It would have been a lot easier. I agree if they gave you KSP, but you kind of have to like, I guess the whole point was to like infer it. I don't know.
Memorize the solubility rules.
Yeah. You really have to.
Memorize.
the solubility rules,
I
Like
mean,
know them,
you should
Yeah.
know them.
but for.
You should be high.
are you gonna take the MCAT?
Yeah, you know them if you wanna take that.
Yeah, if you wanna take the MCAT, no.
Is it gonna be a comment?
It's Thomas's test. He's doing Thomas's test, so it's the same. Hopefully they don't make mistakes again.
All right, any other ones y'all want to go over?
Today, she confessed today that she wrote the last exam like the midnights before, says mistakes.
I'm feeling she uses the same.
Yeah, I
thing.
remember that.
All right, any other problems y'all want to go through?
We can jump ahead, like if there's something that you.
Could we do, sorry, 35?
35?
Yeah, let's.
35. This one, arrange the acids, blah, 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 in order of increasing the acid strength. Okay,
Nice.
so what did we say? We said that what? Acids, the strength of an acid for this class, strength of acids depends on what? What two things?
Electronegativity and resonance.
Electronegativity of central atom and number of oxygen atoms or resonance acids. Number of oxygen atoms. So do you see any oxygen atoms here? Any oxygens? So you can really decline that second point. So really all we're really looking at is the electronegativity of the central atom. Now, if you look at our periodic table real quick, we shall see that it's like arsenic, selenium, and then bromine. So which one has the highest electronegativity out of the three?
Stop showing all my stuff.
BR.
Yeah, Br, we have the highest electronegativity. So if we have As, Se, Br. Br has the highest electronegativity. And arsenic has the lowest electronegativity. So what would that mean for your acid strength? You want something not as electronegative or something really electronegative?
Something really electronegative.
Something really electronegative. So that would make indeed a stronger acid.
I don't know.
Well, if you didn't know that stuff, do we know our 6 strong acids?
Yeah.
Because if you do, then you can realize that only one of those acids is strong, so you can get yourself down to an answer choices of C and D. And at that point, you narrowed yourself down to 50-50 shot. So you, I mean, if you don't know, you can use your deductive reasoning. But I mean, it's also really helpful to understand why and which one, the actual order and why.
So, right, HBr is a strong acid, so this would have your highest electronegativity. Now, look at all these acids. We have HBr, we have H2Se, and H3As. These are H2Se and H3As are what type of acids? Like polyprotic, they have more than one hydrogen. So because of that, remember how for polyprotic acids, you have one Ka. So the Ka of the first is greater than the Ka of the second. Remember that rule? So because of that, if we're evaluating like overall acid strength, which one would you go with here? The one with like 3 Kas, that the third Ka will be like really, really weak, or the one with like 2 Kas, which would be still weak, but stronger than the third one. Yeah, so I'd say H2Se would be slightly stronger than H3As. That's what I'm gonna go with C. Because like the polyprotics, like if you have 3 sort of, whatchamacallit, 3 sort of protons, that sort of decreases the overall acid strength. Because at that point, you don't know which proton you're talking about. So H3As is the lowest, followed by H2Se, followed by HBr.
And also selenium is also more electronegative than arsenic, so it's another reason selenium or H2Se, selenic acid, is more acidic than.
So like HF would be the only exception because it has the highest electronegativity, but it's a weak base.
So
Or
for
weak acid, sorry.
that like sort of thing, like HF versus HBr, you would look at size. And yes, I just said size matters. And in the context of chemistry, it does, because HBr, very large element, so it's able to hold its hydrogen out, like further out. So because of that, that would mean that it could, some unsuspecting base could take the hydrogen a bit more easier. Whereas something like HF, very electronegative, and wants to pull the hydrogen closer, like that thing is not letting go of the hydrogen. So pretty much you could say that HF is pretty weak due to that sort of thing.
Okay.
And besides, if you're looking at an acid, you look at the stability of its conjugate base. So if this hydrogen were to be lost, this Br minus, this negative charge, could be what we call delocalized or distributed along the entire atom.
Yeah, that's what I was thinking about.
38, I have a question.
38, right.
So
Yeah.
I narrowed it down to B and C,
B and C, okay.
but then when did I look for it? If it was like.
Honestly, the amount of growth is really determining how acidic it is, 'cause like H2S.
You still there?
More acidic than HF. It's
So you narrowed it down to B and C.
Yeah, but then I have to find the Lewis.
Why would it not be B?
Yeah, that is, never mind. I don't think I was thinking about it right.
Just make sure,
Because
a
one-
Lewis acid is a hydrogen donor, a proton donor. And a Bronsted acid is.
Other way around, other way around. Yeah, Lewis, think of electrons, Bronsted Lowry, think of protons.
And Lewis acid donates its electrons.
Wait, Lewis acid accepts.
Yeah, it's an electron pair acceptor. Lewis acid accepts electron pairs.
Oh, bro,
Lewis base donates electron pairs.
Right, yeah.
Acid.
Oh,
Yeah,
So.
And Bronsted acid is a
proton.
proton donor.
Exactly.
Yeah. So what do you think the answer is?
I think it's B.
B, so you're
Why?
saying that it's a Lewis base. And so Lewis base makes sense because it can readily donate its electrons due to that negative charge there. Probably has excess of electrons it can donate. And Bronsted acid, well, it can donate its protons too. H2PO4 has two right protons right for the picking. So yeah, option B. I would go with that as well.
When you done, let me do 28 and 36.
All right, 28, and 36.
Go back to 28. Oh, you passed it. Go down.
This is 28.
Go down to the next page because that page, oh wait, no, just kidding. 20, no, stay where you are. Never mind.
Okay, acid dissociation constants for phosphoric acid are given below. Okay, cool. A buffer with a pH of 7.4 can be best made by using what? All right, so what do we know about buffers? Do they change the pH much? So buffers, the term for it is they resist changes in pH. So with that being said, if we look at all of our stuff right here, so H3PO4, the first thing it turns into, if you react it with water, is H2PO4 minus. H2PO4 minus plus. Yeah, that's your base, H2PO4 minus plus H2O plus. Then H2PO4 turns into HPO4 2 minus and H3O plus. So this would be sort of like Ka1, this would be Ka2, and Ka3 will be equal to HPO4 minus plus H2O makes PO4 3 minus and H3O plus. So the thing is with these, you got to look at, well, what is the Henderson-Hasselbalch equation? It's pH equals what? pKa. Yeah, but for our purposes, we don't really care about this part. We're trying to figure out what that part is. So basically, what the question is asking is, which of the following has a pKa closest to 7.4? That's sort of another way you can word these. So what we can do is we can take the negative log of our Kas here to figure out what our pKa is. So if we do negative log of 7.5 times 10 to the minus 3, we will get an answer of 2.12. So that's not quite what we want. Yeah, 2.12. This is too small. So then we'll do another negative log. So negative log of 6.2 times 10 to the minus 8. Remember, we want something close to 7.4. Here we get 7.21. I mean, that's pretty close, but let's see if we can get closer. So I don't think we will, but let's just do it for completion's sake. Negative log of 4.8 times 10 to the minus 13. We get a pKa of 12.32. So of the numbers shown, which of these is closest to 7.4? Yeah, Ka2, so that's 7.21. And which of these is it closest to, or which acid and which conjugate base will be used?
So that would be like NaH3PO4.
That's one half of it, but buffers always,
Wait, sorry, this should be a 2 minus right here. Yeah, that might help out.
but buffers always consist of what and what?
Acid and conjugate.
Acid and conjugate base. So for
It's
acid,
acid plus the salt of its conjugate base.
Right. So it would be the NaH2PO4 and then it should be. I thought it would be HPO4 2 minus, but
Okay, you're onto something.
it is an
Right
option.
there.
It is an option.
right.
Because HPO4 2 minus in an ionic compound would have. Would be up there on answer choice that begins with a letter in the alphabet on the first half of the alphabet? B. Did someone say B? Yeah.
Yeah.
All right, then.
Because look,
Good
if
job.
it's 2 minus, yeah, 2 minus, so it'd be Na2HPO.
Got it, okay.
And right off the bat,
For
you
some
could,
reason, I thought that said in Na2PO4.
yeah. I don't think Na2PO4 wouldn't even exist. It'll be Na3PO4.
Right,
So with C and D, you can go ahead and eliminate them right off the bat as well, because
it has to be 2.
it has to be 2 things, yeah. And then answer choice A corresponds to the first one, but that has nowhere near a pKa of 7.4. And then E, that's the one that's like, it's too big. So, yeah, option B. All right. Any questions about that? All right, 35, right?
6.
36. 36, like the ACT score. All right.
Like your ACT score.
What is the pH of a 0.2 molar solution of NH4Cl? And your Kb of NH3 is 1.8 times 10 to the minus 5. All right, Kb, and they're giving me NH4Cl. So right off the bat, what's the first thing y'all would do?
Change it to K,
Why?
because we're dealing with an acid.
What part about it is acidic? The CO.
Isn't the NH4 acidic?
Yeah.
Yeah.
Yeah. The NH4 is indeed acidic. So let's change this from the Kb of NH3 to the Ka of NH4 plus. And how do we go about doing that again?
What should divide 1 times 10 to the negative 14 divided by 1.8 times 10.
1 times 10 to the negative 14 divided by your 1.8 times 10 to the minus 5. Having solved that out, we get 5.56 times 10 to the minus 10. That is our Ka. So if that is our Ka, and we have a pH of 0.2 molar solution, what will we go about doing next?
0.2 mole.
So we're going about solving for a pH with a concentration of 0.2 molar. There we go.
So can't you do x squared over moles equals to Ka?
Yeah, that's what I would do.
I
So
would skip the ice box.
just skip it. Ice box.
Ice table.
That is that is a weird. I can forgive like ice table, but ice box, bro. All right, x squared over 0.2. So your initial concentration. And again, this is sort of like a shortcut you could use without doing the whole rice table stuff. Because you only have 50 minutes for the exam, so every minute counts.
How do you know you can neglect X, Rich?
You know you can neglect x because you can take the initial concentration of 0.2 and divide it by your Ka here, 5.56 times 10 to the minus 10. And that will definitely give you a number greater than 400. So you can neglect x.
I thought, wasn't
There's
it
a
like
400.
5%?
That's sort of the same thing, but I like to use the greater than 400 because who's going to compare the decimals like 0.05 whatever, as opposed to like 400, you know?
Has there ever been a problem where we didn't neglect X?
Well, not for the
Yeah, not for.
not for the acid base stuff.
Yeah, 'cause
Okay,
I-
so can we just assume for this test that we don't have?
I mean, we're not going to tell you as much as I want to say no. I mean, as much as I want to say yes, no.
Yeah.
Because if you go to your professor and say, well, the TAs told us
Yeah.
to assume
Oh,
it
it's
as 0, then it's gonna, yeah. So no, you cannot assume.
It's a liability for you.
It's like you didn't hear it from me, but you can 90% of the time. 90%.
Credit for Rich.
I'm wanting to put my money where my mouth is. All right. So
Those who-
we got our X concentration, our hydronium ion concentration. Once we do that, we get 1.05 times 10 to the minus 5.
Wait, oh, this is regarding the test. How many questions are on the test? Says we're only
2025, something like that.
we're only getting 15 minutes. Like, are we gonna be able to answer like everything though?
Yeah, we were able to answer everything. I mean,
Doing ice table is crazy.
She told us today there's 23 questions, I'm pretty sure, and like 3 free response or 2, I'm not sure. And she said that like
Only 3?
it's, yeah,
That's it?
and she said that it's out of 115 points. So it gives you 5 questions to still get an A on. So like if you miss 5, you can still get an A, which is like
I'm still
And
getting.
if you do your Alex extra credit,
that's an extra. 5.
No,
that's
Berta,
120.
Our class changed instructors, so the rule changed.
You also have +10 bonus points. Or what do you have now?
For what?
It's
What's the odds?
Did y'all ever get, wait, y'all on Zapata, are you on Zapatas?
Yeah, we didn't get +10.
How much y'all get, +5?
No, we got Alex and.
What do you give you for Alex? What do you give you for the Alex?
+5, but then he gives us a grace of like 4 days.
Last semester he was going crazy.
You still don't raise this, bro. He give you crazy.
No,
What do you think?
The curves are-
I +5 for Thomas, but
Oh,
then she
right.
gives us no grades.
All right, anyway, 1.05 times 10 to the minus 5, that's your hydronium ion concentration. So if we negative log that, what will we get? Little thing called pH. So if we negative log our 1.05 times 10 to the minus 5, we will get an answer of 4.98, which is equivalent to answer choice C.
So I have a question. So let's say this was asking about like base. Can I just subtract after I get pH because
We get POA.
I know POH for like base.
I mean, I guess that's
Well,
Wait,
oh,
no, no,
would
you would
have
have
to slug it in?
Negative log of the OH concentration, it's you POH, and then you have to do 14 minus the POH.
Okay, so you can't just like subtract 14 from acid.
Well, I don't think you can use acidic concentration with the KV.
Um,
I don't think you would get, I don't know, I could be wrong, I've never
So if
experienced
you were
it.
to find, let's say this was about a base, you would just use KB and then find POH and then subtract.
Subtract
it.
14, yeah.
If it was about a base, but in this
Right.
case, it's
This is
about
about
an
acid.
acid, so yeah.
Yeah.
For the whole neglecting X thing, you're saying that the number is greater than 400.
Yeah.
yeah. So if you have the initial concentration over Ka or KB, and if it's greater than 400, you can neglect your X.
My rule is -5.
I always
Like if
neglect
your
my
K is a -5 or higher.
I didn't know, like, I never heard the 400 one, so I was like.
I'd say -5. That's whatever, 400 -5, whatever.
We use Insolver and call it a day.
I mean, you can't use that.
Insult.
Because graphic calculators are not allowed.
Whatever value that you get, this value.
Maybe. maybe not.
But if you got one of their OG calculators.
You get the job done quick.
That is obviously greater.
No, get the TI, they're much better than this thing.
Oh, is that what you're saying?
Guys are slow.
This guy and his TIs.
Let's see.
All right, what other questions? Y'all have the PDFs with y'all? Is there any other questions that
So the initial
are,
concentration.
are like, what the heck do I do here?
Greater than 400, neglect your X.
Or is that just the whole packet?
And if it was like,
If it was like base, it would be like that over KB.
Yeah.
Can we do a titration question?
Michael Delir, wait, Michael Duro said 29.
29.
Not.
I saw delirious.
This is buffer.
All right,
26 is titration.
20 milliliters of NaOH. solution. Okay, that's sort of the same thing we did,
yeah, okay. no.
Yeah, that's one I did.
yeah. It's sort of the same thing, but remember, right, if it's NaOH, will it react with the acidic or the basic part?
You all have like steps to like the first thing that you do is identify if it's like strong acid, weak base,
I
and
think
then
it's right the, you talking about for these kind of questions? Or what are you talking about?
titration buffers.
I'd write the reaction, so like, you know, like exactly, so you, like his question right now, you have NaOH and you have a buffer of acetate and acidic acid. Well, NaOH is acidic or basic? Basic, so is it gonna act with the acetate or with the, what is it, acidic acid? The acidic acid, so he's writing it out right now, just like that.
Yeah.
Like, that's the first step I always do with titrations, just write out what I got.
Then instead of that, you could always use the A and A.
Yeah, I use HA and A minus, same deal, yeah, that's what I do.
Yeah, I like to write it all out just for the
So you can
continuity.
see it.
I mean, if they want to take off, I mean, some professors have like, I don't know, sticks up their asses and they'll be like, what's, and then, they'll be like, what is this HA right here, -5? So
Oh,
for like for continuity purposes, I just like to do the entire thing.
Like on the pre-response.
Like, no, it's just, it's not pointed at any professor like specifically. I'm just like me personally, how I run is like, I don't give them any room to pick up points.
Still loses points.
Actually, I do better on the free response than I do on the multiplication. choice.
Do they give points? Like, do they give, you have to get the whole question right to get points on free response, or do they give you? You get partial? Yeah, shit.
If I remember right.
I don't think.
I'm
they-
pretty sure it's partial credit.
For the previous.
Part of last fall, all we had was multiple choice and 15 points extra credit, you know? We didn't really do free response. in my day.
Oh, plus the 50-point curve.
Exactly, after the 60-point curve, actually.
Oh, okay, man.
That's fair. Well, kind of,
But you're not playing.
huh?
He took a.
Oh, he was just feeling great, you know? He was good, he was a better.
Last semester was the difference.
It's suspicious because if you, let's be honest.
All right, and anyway, back to the rice state. So what is our initial concentration of acetic acid?
Okay.
What is it equivalent to?
You go through the moles or concentration?
I do either or.
I just need those first.
All right, let's do moles first. Let's be different.
Oh, you can do that too.
So, all right,
So when do you use the moles and when is the polarity?
so
Like in an ice table?
generally I use moles only when it's before the equivalence point of a titration. Any other scenario is polarity, but in this case, I guess you could use moles as well. So, yeah. So, all right, so if we were to do the moles, what is our initial moles of acetic acid? What would that be?
Over.
It would be 0.3 times 0.5.
0.15.
0.15. Sounds good to me. All right, what about our CH3COO? What is that? Point
So
two,
what was that?
Oh my God.
You do this one in your head.
0.2 times 0.5.
With 1/2 of 0.2.
0.1.
That's
One.
good.
All right, now what's our moles of OH? Last piece of our puzzle.
1 times 0.0. What is that?
0.2.
Very good.
All right, now for our OH,
God.
our base is limiting. So if we subtract our 0.02 from here. And so we'll subtract it here as well. What do we do to our 0.02 on this side? So 0.02. So this will be equal to 0.1 plus 0.02. This is 0.12. This is 0. This is 0.13. All right, now as OD did with the acid one, we can toss this into the Henderson-Hasselbalch, right?
Yes.
Is he missing something?
Am I
We're
missing
missing the PK.
Yeah, it's concentration. Yeah, so you divide it by total volume, so that's 500 plus 20, so that's 520, so that's 0.52. I'm gonna divide this each by 0.52 liters. And if I do that, so our new concentration of CH3COOH after the addition of our sodium hydroxide. So this is 0.25 right here, and this one will be very close to that, I can imagine. Yeah, 0.23. Now we can toss this into the Henderson-Hasselbalch, right? All right, so pH equals pKa plus the log of conjugate base over acid, A minus over HA, whatever. I'm using A minus, I'm using HA. So A minus, right? Log of 0.23 over 0.25. Then what's our pKa of acetic acid?
You don't have it memorized?
We had it in lab, but I forgot.
Never mind.
What,
That's
2
2 points higher than that,
4 point something?
4 point something, 4.74 specifically.
We could have just converted.
Yeah,
Once you get to OChem 1, you're gonna be thinking PKs.
yeah, you need to memorize all of your pKas. Acetic acid is one of them.
It's not that bad. It's not that bad.
All right, so you log 0.23 over 0.25.
Well, at least for that. Sure.
All right.
Everything else we say.
Solving everything out, you will get a pH of approximately 4.704, which I would say is close enough to answer choice E, 4.71. There's probably some rounding or something there, like pKa of acetic acid isn't exactly 4.74. There's probably like 4.74, whatever, to the decimal point. So because of that, you can say confidently that your answer choice is 4.71.
I laugh at myself for the mental math stuff because today I was in my research lab and my mentor was like, okay, now go dilute the PBS fluid. We need to make it you have 10 times, you need to make it a 1 times. And I was sitting there trying to figure it out. I was like, just do it in your head. I'm like, I can't do it.
All right. Yeah, that is
You in a micro research lab?
Use that.
I'm in neuroscience.
Okay.
all right. Patrick has requested question 19.
Question 26 before.
26.
All right, we'll do 26. All right, 50 milliliters of 0.1 molar nitrous acid is titrated with 0.1 molar KOH solution. After 25 milliliters, the KOH is added. The pH of the titration flask will be what?
Very similar to the last one we did.
All right,
So send them up.
so for these, first thing I do is look at where I'm at in my titration. Am I before my equivalence point, during my equivalence point, or after? So for that, I'll calculate my moles of acid, my moles of base.
Okay.
So let's calculate my moles of base first, because it's that's the one I'm staring at right now. So I'll convert my milliliters to liters, so 25 over 1,000 times 0.1. So if I solve that out, I will get an answer of approximately 2.5 times 10 to the minus 3. That's my moles of base. Now for my moles of acid, similar sort of thing, 50 over 1,000, 50 over 1,000 times 1. So if I were to solve this out, you'll do 50 over 1,000 times 1, and you would get an answer of 5 times 10 to the minus 3. So which one's greater, your moles of acid or your moles of base? Moles of acid is greater than your moles of base. So does that mean, where are we at in our titration?
Wait, that's wrong, because isn't like 5 times 10 to the negative 3 less than 2 point? No?
So you could just look at it like, get rid of the 10 to the negative 3, look at 2.5 and 5. Which one's bigger?
Okay. 5 is greater.
Yeah, because they're both the same power. Yeah.
So moles of acid is greater than moles of base. Where are we at in our titration?
Isn't that like at the beginning?
Yeah, so would that be before the equivalence point? So it's before the equivalence. Or equivalence. So before the equivalence point, we can use our handy little equation, Henderson-Hasselbalch. So to do that, first I'll write out my equation. So HNO2 plus OH minus goes to H2O and H2O and then NO2 minus. O2 minus, go cross out our water because it's a liquid, doesn't really count. So HNO2, we already have our moles for that. That's 5 times 10 to the minus 3. And for our moles of base, it's 2.5 times 10 to the minus 3. So which one's our limiting reactant, our acid or our base? Which one runs out first?
Base.
Yeah, the base. So we can subtract 2.5 times 10 to the minus 3 minus 2.5 times 10 to the minus 3. So here we'll add 2.5 times 10 to the minus 3. So our new conjugate base moles is 2.5 times 10 to the minus 3. And our leftover acid is, I think, 5 times 10 to the minus 4. Let me check. 5 times 10 to the minus 3 minus 2.5 times 10 to the minus 3. That would be equal to 2.5 times 10 to the minus 3. It's the same thing, 2.5 minus 2.5.
Then we're gonna divide by total bulk.
What do you say?
So our pH equals pKa plus the log of A minus over HA. So since our A minus and our HA are the same, this is over 1. And what's the log of 1 equal to? Log of 1 is indeed 0. So our pH equals pKa. Now, what point at our titration are we at? There's a specific point we're at where the pH equals pKa.
Check them 2 left.
The half something.
Oh. Is that?
Yeah, the half equivalence. So we're actually at our half equivalence. So our pH equals pKa. So I did all this work for no reason. So to find our answer, we can just negative log our Ka to get pKa. Negative log of our Ka, so it's negative log of 4.5 times 10 to the minus 4. And we should get an answer of around 3, see if that's true. Negative log 4.5 times 10 to the minus 4. Yeah, 3.35 is our pH.
I have a question.
Let's see.
Why didn't we divide by total volume after we got like the?
So here's the thing. This is the one exception you can make by using moles in the rice table. Because normally you're right, you would divide by the total volume. But look at the total volume here. It's the same for this thing as it is for this thing.
Yeah, that's
So if you divide by the total volume, it's like dividing by the same thing. So it cancels out.
okay.
Yeah.
Well, see more.
I think you just said it, so not a emails.
And we all want to take number 19.
19?
Yeah.
Oh, you want to do 19?
Thank you, Patrick, requested it.
I think that'll be our last one.
Oh, but.
Oh, no, it's not that bad. Yeah, Sam taught me how to sortation.
Okay, so. Minimum concentration CRP plus be added 0.095. So first thing I'm gonna do is write out what this is, CRF three. Then I'm gonna be looking at, we have right here. No. So let's write out our KSP. KSP is equal to X, 3X cubed. And also at the same time, so let me write out the thing, we have CRF3 turns into CRF. You with me so far? So like, I'm just now writing this out, and then we already know that this is a solid, so we can kind of ignore this. So then our initial for the CR is 0, but our initial for the, what's the initial for the fluorine?
Fluorine is 0.09.
0.095, the change minus X. No, I'm sorry, plus X, and then plus for the fluorine, how much am I adding? Plus what?
Plus 3x.
Plus 3X. And then the equilibrium for the chromium is gonna be X, and then for the fluorine, that's going to be 0.095 plus 3X. So then all we're doing now is slapping that into the KSP. So KSP that was given 6.6 times 10 to the negative 11 is equal to X 0.095 X plus 3X, sorry, cube. So then let's get what our X is. 6.6 times 10 to the negative 11 is equal to X 0.095 plus 3X cubed. And we're getting an X value of, X is equal to 7.69. So first of all, are you with me? 698 times 10 to the negative 8. You with me?
Yeah.
So, okay, cool. So we can see here that the chromium, that was our X. So if we get our KS or our concentration of X to be 7.698 times 10 to the negative 8, that's the same as the chromium. So here I'm getting 7.7 times 10 to the negative 8, which is D.
Basically, kind of like the constant equilibrium expression.
One more time?
Is it like the constant equilibrium expression kind of thing?
Yeah, pretty much. Yeah, exactly. Yeah, exactly, pretty much. You just have to break down the thing, yeah, from the solid form. Pretty much, man. So KSPs, how you feeling about them? They're not bad, I mean,
It doesn't feel that difficult.
I mean, everybody cool until you get 108 X up in.
Oh, yeah, that's interesting.
oh shit, is that to the fourth? What is that?
That's when you have like five.
Oh, 3 and 2? Oh, yeah.
Like 3 minus
3 and 2.
Lazy, and instead of giving us like, answer choices with variance, like numbers, she just changes the power to.
All right,
So that
so
gets tough.
for people on Zoom, we are done. We have some things to take care of ourselves. We would love to go. A
All
little
night.
bit longer, go into the night. But unfortunately, I know y'all wanna go eat dinner too. We have to do homework. Y'all are free to go.
And then another thing, really important thing, this is gonna be a weekly thing, so y'all free to come in every Monday, 5 to 6. This is gonna happen weekly, not just for exams. So yeah, with that, y'all have a great rest of your Monday.
I don't see the points in like doing a battery lab, so okay. I'm just doing it just.
This guy's saying, all she has to do is take OChem 2 lab and she gets her minor in chemistry.
I have a good one.
Cause it can be like.